The earliest phases of the Big Bang are subject to much speculation, since astronomical data about them are not available. In the most common models, the universe was filled homogeneously and isotropically with a very high energy density and huge temperatures and pressures, and was very rapidly expanding and cooling. The period up to 10⁻43 seconds into the expansion, the Planck epoch, was a phase in which the four fundamental forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, and the gravitational force, were unified as one. In this stage, the characteristic scale length of the universe was the Planck length, 1.6 × 10⁻35 meters, and consequently had a temperature of approximately 1032 degrees Celsius. Even the very concept of a particle breaks down in these conditions. A proper understanding of this period awaits the development of a theory of quantum gravity. The Planck epoch was succeeded by the Grand Unification epoch beginning at 10⁻43 seconds, where gravitation separated from the other forces as the universe's temperature fell. At approximately 10⁻37 seconds into the expansion, a phase transition caused a cosmic inflation, during which the universe grew exponentially, unconstrained by the light speed invariance, and temperatures dropped by a factor of 100,000. This concept is motivated by the flatness problem, where the density of matter and energy is very close to the critical density needed to produce a flat universe. That is, the shape of the universe has no overall geometric curvature due to gravitational influence. Microscopic quantum fluctuations that occurred because of Heisenberg's uncertainty principle were frozen in by inflation, becoming amplified into the seeds that would later form the large-scale structure of the universe. At a time around 10⁻36 seconds, the electroweak epoch begins when the strong nuclear force separates from the other forces. With only the electromagnetic force and weak nuclear force remaining unified, inflation stopped locally at around the 10⁻33 to 10⁻32 seconds mark, with the observable universe's volume having increased by a factor of at least 1078. Reheating occurred until the universe obtained the temperatures required for the production of a quark-gluon plasma as well as all other elementary particles. Temperatures were so high that the random motions of particles were at relativistic speeds, and particle-antiparticle pairs of all kinds were being continuously created and destroyed in collisions. At some point, an unknown reaction called baryogenesis violated the conservation of baryon number, leading to a very small excess of quarks and leptons over antiquarks and antileptons, of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter in the present universe.